Hello everyone, I'm going to take a second and talk about binary and how it's represented in data. Before I get too deeply into this though, just as a reminder, this is meant for a beginner audience. The content and the material that I will cover is very elementary in nature. It's meant for someone who's just getting into the cybersecurity career field or the intelligence career field and is in an apprenticeship program or in similar kind of circumstances. Though, admittedly, if you are in this field and you work in this data and you don't touch this daily, you might see a thing or two that may jog memory and make you remember a few things that you find helpful. So if you are already experienced or a 10-year veteran or more, you may not find a lot here, but please join us anyway. If you are new, please take in as many of the concepts as you can and do additional research. I'll provide some links that will explain a few more things and kind of give you a couple more items to dig into when it comes to binary. All right. It's always, in my opinion, good to take a second and mention that much of our work revolves around recognizing data, especially patterns in data, and recognizing data in what form it's in, and kind of knowing how to convert it back and forth to try to get the best view possible. In fact, a large portion of DFIR, if you're not familiar with that term, Digital Forensics Incident Response, and intelligence does exactly that as a daily task. So that leads me to answer this question that often comes up. What is binary? Most people these days don't necessarily ask that because in their head they're very familiar with this concept already, but it is effectively a 0 or a 1. In fact, all computer data is stored as a 0 or 1, and each individual piece of that, either 1 or 0, that's being stored is called a bit. And when it comes to terminology, that's something you want to remember because there are so many bits. Each bit will be a 0 or a 1. And in fact, binary gets its name from this very fact. The common unit you will hear people refer to this in is bytes, which are, of course, 8 bits. I say of course because if you haven't dealt with this, they may not be incredibly obvious, but there are 8 bits to a byte. Now, why there was chosen to be 8 over 10 is kind of practicality and history. So I'll start with the practicality part. Because computers store data in binary, performing calculations or manipulations of base 2 is the most efficient way for them to use data. And if you think about base 2, so 2 to the third power is 8. So 8 is in that sequence of 2, meaning it would be faster than 10, which is absolutely not. It has to do a second or additional calculations to figure out something that is set to base 10. Well, that's one of the kind of practical facts behind why they chose 8 for the byte size to be the most common and elementary unit out there versus 10, even though we have 10 digits and 10 toes, and it's very common for us to think of things in decimal, which is 10 base. Historically, if you go back, there was no unification on what the size of a byte was until relatively recently, about 40 some years ago. And part of that was because different computers were being created in the 50s and 60s, and before that a little bit. In fact, all the way back to the 800s, they were debating on the size of memory, basically, and what was a definable unit, even as far back as when we had punch cards. And so if you fast forward through to the 50s, 60s, where big mainframes were coming out, IBM was big in the space, as were other players, and they're trying to define what the best addressable unit of memory is. And they settled on 8 because they already had a mainframe that was doing really well that had that particular byte size, utilized. And they wanted to base things on their most effective way forward. And so by dominating the market like they did during that time frame and pushing forward with kind of an 8-bit definition for bytes, they were able to kick people off and get out of the way and unify everybody behind the idea that there are 8 bits to a byte. In many ways, it's like the Betamax and VHS war. It wasn't necessarily the best one that won, but it's definitely the one that we use these days. Not that anybody really uses VHS anymore, but if you're not familiar with that incident, go look that up. That was an interesting time, and it kind of is very typical of some of the things that we take for granted today, that they're in X form, even though before that definition was solidified, they possibly had many, many, many shapes. All right, just as a kind of fun side note there. Let's get into bytes again. So again, bytes are relevant as a unit because they are pretty much the smallest addressable unit of addressable memory. So when you look in memory, we don't talk about things to the bit level. A lot of times when we're looking at computer programs as analysts, or you're a developer building these, you don't talk about, I'm going to move just a single bit, unless you're working in assembly still, which there's plenty of use cases for that. Majority of the time you're moving bytes around, and in fact even with assembly you're pushing bytes around because they are the best unit of addressable memory to use. Kudos for anybody who can kind of decode what that binary is. It does come up to a word. Bytes, while we're talking about them, are always read completely, not by their individual bits. So when memory is read, again, a byte is the addressable size, so that it has to be at least that unit. So you're not going to say, okay, I'm only going to read this one bit. You're going to read the whole byte, and you're going to read the whole thing. You're not going to read only half of it. Kind of keep that in mind. That'll become important later, especially in later lectures when we talk about the analysis of this kind of information. But just know that bytes are the smallest addressable unit of memory that can be read and used. And by default, most information is encoded in bytes, not in bits. You'll see I made a compression note there. Compression has one agenda. Compression wants to shrink down and make as small as possible whatever file it's being used against, or files. And a lot of times I like to give the example of shrink wrap. If you've ever used a shrink wrapping machine, you put something inside there and you put a bag around it, and then you shrink out, you suck out all the air and you shrink it as tight as possible to the object you just put in there. Compression does this, but as well, many compression, in fact almost all of them, will also rearrange, it will disassemble, rearrange, and recompile what's there in some fashion to, I guess recompile is a bad word, they will reassemble whatever's there in some fashion to make it as small as possible and then shrink wrap around it. And they do that so that they can have the best compression. So something that has super high compression, will do many, many more things. They'll remove blanks, they'll remove nulls, they'll remove empty space, they'll remove everything that you might think is human readable and replace it with mnemonics and pointers and things like that, so that it can compress as much of that space, remove what it considers wasteful use, until it gets down to what is the best object it can create, that is smallest. That's why you have some compressions that were able to shrink files more than others. And sometimes there's loss during that process. So, compression is its own interesting talk to get into. All right. Not only knowing binary exists and bits and bytes and so on, you kind of need to know the others, the kilo, the mega, the giga, and so on. And it goes on exponentially. Just look up the metric versions of that. Past terabytes, for example, you get into petabytes, and then you get into exabytes, and it just grows. It's just an easy shorthand way to reference the size. Now, it's important to also know that size represents a value. And when I say value, I'm talking about the amount of possible things that can go in that equivalent space. So if I had to use 8 bits to make a byte, that means I have 256 possible values that could be explored or put in that 1 byte of memory, or that 1 byte of space. And if you need some things to think about when you bought your computer, a lot of times you're like, or your phone, you're like, hey, I want a 256 gig phone, which means you want to have that much space in there. And you could have an enormous amount of values that could be put in there. And so in this case, like you take a single byte or 2 bytes, you can see that the bit values go up. It becomes relevant for us in a couple ways. So if you're a developer, it's wonderful if you have a large flexible space in which you can put anything in. That makes storing information and retrieving information very much more comfortable than if you have a limited restricted space or a really bad mechanism in which to put information in and pull information out. As an analyst, it can be a little prohibitive if it's just a large flexible space, because we have to ask how many values could potentially be put in there. And values define the search space of what you're trying to find. So if I see a byte of information, for example, and I'm trying to figure out what that byte is, by default, there's going to be 256 values in there. Any single bit I can identify reduces the number of possible values exponentially by an exponent of 2. as you can see. So the 2 to the 8th power there, if I can find one of those, it automatically gets reduced and the number goes down, so that I can try to figure out exactly what's in there. Maybe that wasn't clear. I can come back and re-describe it later if need be. Just leave a comment in case it isn't. Key thing I want you to remember is that the value size will always equal an exponent of 2. And if you can figure out how many bits are in the amount of space you're looking at, you can figure out how many possible values are there. And then if it increases or shrinks, you can lower the possible amount of values by one exponent to kind of either reduce it by that much or double it if you add 2. All right. Here we go. Another point that's really important to make is that this is zero based. So when we say 256 values, you're going to see 0 to 255, which probably isn't a surprise because if you think about how IP addresses are set up, they go from a range of 0 to 255, showing that they have 256 values at each octet. And they have many other things that I'll skip at the moment. Go back to the IP presentations if you're curious about that. But that's kind of important because if you're curious about how big an IP can be, well, there you go. You can only have so many values in each one. But back to a byte, just know that it is zero based. There is 0 to 255 values in each, or 256 values in that range, and the range is 0 to 255. Again, hit me up with questions if that isn't clear, because that can be confusing at times. And just know that binary comes in many forms, even though we may not call it binary. So binary pure, that 0100001 over there on the side. Decimal is a form of binary. We're just representing the data with a 10 base, so like the number 81. Hexadecimal uses a base 16. Then ASCII, which we're all familiar with and reading on the screen. And of course, base 64, which uses a 64 base character set in order to define different ways of expressing binary. It's important to us because we shift back and forth between these. And by knowing, again, back to values and size, you kind of want to keep an eye on your size. So 64 bits and 128 bits are kind of really important ones. As you can see, there's enormous size. That's why that has the E in there for the exponent. And so when we, on our end, a lot of times it's shrinking the amount of things we need to look at by inserting things we know for sure are there. Allows us to directly reduce our search space values for what we might want to find. But let me get back to topic here. So binary, straightforward, zeros and ones. I mentioned hexadecimal. Instead of each digit representing 10, and yes, I'm skipping decimal because everybody's very familiar with decimal. In hexadecimal, as it sounds, hexadecimal, so it's 16 base. So instead of continuing on with numbers, we use 0 to 9, and then we start using letters A to F to go above 9 to 15. So it's 0 to 15 or 16 values, as you can see here on the right in the table. You can use that to a lot of things. There's a concept called Ascii Armoring that is really important. That's a term you want to write down and kind of look up. It kind of drove, even though it wasn't called that in many instances, it kind of drove the creation of many different base code structures. Like ASCII itself was created out of a need to define a certain palette or a certain baseline of characters that would be used. Hexadecimal does the same thing. And hexadecimal, in fact, you often see hex when you're looking at URL strings and things like that because the Ascii armoring piece comes into play. The concept behind Ascii armoring is if you push everything in plain text, especially through URLs and other transactions, the text in there tends to conflict with the actual commands, the functions, and things that you're trying to call. So to prevent the data being passed from being contaminated or misunderstood, you armor it against that kind of activity, hence the word Ascii Armoring. And so if I take URL and I assign a value and I convert the value that it's being passed into base 64, there's less chance that there will be a conflict on the receiving end or anything in transit. It also minorly kind of hides that information a little bit. So in this case, continuing on with hexadecimal since I got off topic, single hex digit represents 16 values, which is a nibble. It's only 4 bits. So if I want to represent a byte, I need to use 2 hex digits like MZ or 4F. So very typical. If you look at things in a hex editor, which is short for hexadecimal editor, you would see things in nibbles and bytes. So you'd see 1 hex digit would be half a byte, 2 hex digits would be a full byte, and so on. So if I want to do, and earlier I was talking about trying to define what is in where and how much searching I'd have to do. So if I had a 2 hex digits like in my MZ here, if I had the M but not the Z, I could define that, okay, I have 4 of those bits determined. I have 4 bits I need to figure out, which means I have 16 possible values for the next piece, one of which could be the hexadecimal value for MZ. So keep that in mind. And of course, it's worth noting on hexadecimal, since we use it all the time, frequently we refer to things as 0x, so 0x3f. We're making a kind of prefix shorthand for it so that you don't get confused with me saying 3f. By the way, back here on this previous slide, you can't actually put MZ down in hex. That's a mistake. I'll correct that in future presentations. If that bothers you, leave me a comment and tell me all about it. That's fine too. But I realize that that would have to be represented in a different way. But 4F is correct. So context is everything, which is why I went back and explained that. It's very good. Even though you may see something and you see an equal or equal at the end of that string, you're like, oh, that's base 64. It may not be. Never assume how data is encoded. Always verify and check as much as possible, because that could actually be a different kind of encoding that's just set there, that's trying to throw you off, and the equal could just be a red herring. Very common in malware. Of course, I mentioned Ascii a few times. You have to talk about it. So Ascii is Ascii because of a lot of reasons. Honestly, it takes 1 byte, though really only uses 7 bits of those 8 bits that are there. That 8-bit is kind of reserved. If you get into the extended Ascii table or you look at different code bases, they have taken that space to use to kind of throw out different symbols, different characters for language, and so on. So it kind of has its place. Having this handy, especially with the conversion from decimal to hex to text, is very useful. That way, if you want to, like someone has URL encoded something and you're looking at a %20 and you're like, why is that there? You can go and look it up and figure out why, because that's a space. If someone has done something similar, such as with a double quote or a period or anything like that, you can go look it up and so on and so on. So, I mean, this is a very useful table. You can find this table anywhere online. I can also put a link to a couple of them for you in the text below. So having one of these handy, especially when you're decoding things, is useful. Now, personally, I don't use this table anymore. I use CyberChef. I definitely will have a link for you for CyberChef. You can use CyberChef locally or online. It has everything I've talked about plus on steroids, and does a great job of allowing you to tinker, tailor, and kind of manipulate things back and forth. In fact, I highly suggest you go there and practice. In fact, practice is everything. CyberChef will be your online tool, and I'll put a link or two down there for you to play around with. Get there, practice moving text back and forth, changing from, especially, we'll go back one here, from hex to text or back to decimal, so that you get very familiar and comfortable with that kind of conversion. So thank you for joining me on this talk. This concludes like the basic, very basic introduction to binary and kind of some of its data representations. We'll build on this and talk about more in future lectures. Before I go, if you like this, please give us a like. If you enjoy what you're seeing and like the content on the channel, please follow us as we develop and create more information for folks who are beginners and new in our industry. Thank you for your time.